नहीं कुरा मैंने चार्जर देई। हेलो।
Hello?
Okay, we are going to start our discussion from the question we have left when we are doing. So here we have the question number. You can see that we are going to start the question number 35, which is about the 36. So I solve first part, and in second part, in first part, we have to show that. Hello, do you want?
Yes.
Do you listen me?
Yes, I'm here. Yes, yes.
Okay, we have to show this is linear mapping, and then find kernel images, and then we have to solve this equation, and then we have to check that whether the its rank nullity theorem, dimension theorem, is applicable or not. First of all, you have to understand what is this c1 of 0 means. That this c1 of 0 1 means that space of all the function which are differentiable. So for the differentiability, there are the many functions, so we don't understand what is the its domain dimension. So in this case, the dimension of the transformation is infinite. So when the dimension is infinite, then the dimension theorem is not applicable. Dimension theorem is valid only for the uh, finite dimensional space. So it's an infinite dimensional space. That's why this vector space. That's why this transformation does not applicable the dimension theorem. And the next one is how to prove it, whether it's a
So,
transform.
uh, hel- so, so if it's C1, it's not applicable.
No, it's a dimension theorem is not applicable.
Yes, if it's C1.
Yes.
Okay.
Now we are, as I told you, in 36. First, he check the property of f of x. Given we replace f of x by kf by plus lg, and then we separate these f prime and 2 and this, and then this is the common. K is common, then t of f, and then l into t of g. So linearity is satisfied. In the second step, we have to find the kernel and images. For kernel and images, we just put t of f0. So as he gives you f prime of x is equal to 0, so it's equal to 0 when we integrate on both sides, so that we find the value of x. So we integrate on both sides with respect to x, so we get here its derivative and integration cancel. We get here f of x, and in this the integration of 0 is a constant, so the function is constant. So here the we get the constant function in kernel of t. Kernel of t contains the constant function. As you have like a function, we have 2. When we take its derivative, then the derivative of 2, we know that it's 0. So that's why the function is 2. The function is f is constant. So the kernel of t is the set of the constant function on 0 1. Is it clear?
Yes.
Now we are moving towards the images. Images means that the answer we have obtained. So it's the answer t of f is we have images of t is the set of all the values for which g belongs to 0 1, such that there exists a f. So value of f t at f is equal to g. So when we put the t of f, we get the f prime of x, which is equal to g of x. So we obtained this. We integrate both sides. F prime of x into g of x, dx is equal to g of x into dx. So we have obtained this result. This becomes the f of x, which is equal to integration g of x into plus c. This is our images. So our image is the integration of the function g, integration of the function g plus c, which is the constant of integration. So t of f is the function g plus constant. So its images of t is the space 0 1. In the next step, third step, we have to solve this equation. What is this equation? This is the 1 minus x square, and as we know that t of f is equal to f prime of x. So I replace it's f prime of x. So from this equation, we can put it equal to f prime of x. F prime of x is equal to 1 minus x square. So we integrate on both sides. So this becomes f of x, and this term is the integration of one is the constant is the x, and the integration of x square, which is x3 divided by 3. So this is the solution of this equation. And now when we do the integration, then we always put the constant, which is constant c. So we obtained x minus x3 divided by 3 plus c, which is the constant of integration. Is it clear?
Yes.
Now you can also see here we have this, and he finds that x minus x by 3 plus c, which is the constant of integration. And the d step, he says that the dimension theorem holds. So dimension theorem does not hold, cannot be whole applied, because the dimension of the domain of t is infinite. That's why it's not applied. Dimension theorem is only applied when the dimension is finite. Now we are moving towards the 37, which in which he gives this mapping t of p is equal to this, and he says that find an orthonormal basis in images of t by using the inner product of c naught into minus 1 plus 1, and compute the t minus t into 1 minus x. I leave this question because first of all I have to told I have to clear your concept of orthonormal basis. What is the basis, then how to make it orthogonal, and then how to make it
Oh, yes, yes.
orthonormal. So we start, we do the question like this. In the question like a 38, we are moving toward 38. This is this question. He gives this transformation. He says that show that it's bijective. So first of all, to check its bijective, we make its matrix. When we make its matrix, then 1, 1, and 1, the coefficient 1, 1. Sorry, the coefficient in the, we get this we 1, 1, and 1, this coefficient 1, 1, and 1 here, and similarly the coefficient of this terms. So it's a 0, 1, and 1, and the coefficient of this is 0, and it's
What
0, and it's
is it? Is it column or row?
we write it into the column form
Every time?
every time.
Okay.
So we have obtained this. Now our task is to make this element 0. So how can we make this element? First of all, I replace this 1, 1, and minus 1, and this becomes 1, 0, 0, and this becomes 1, 1, and 0. Now I apply the operation. I have to make this 0, this 0. I subtract it from it. So it's becomes 0, and it's also becomes 0, and it's 1 minus 1 also becomes 0, and here 0 minus 1, it's become minus minus plus 1, and similarly it's 0 minus 1, here is minus 1, and here is plus 1. We got the matrix into this form, like you like I am writing 1, 1, and minus 1, and then 0, 0, and plus 1, and then we obtained the 0 minus 1, and it's 1. Now we replace these two rows. We get I get 1, 1, and minus 1, and this is the 0 minus 1 and 1, and this is the 0, 0, and 1. This is the row echelon form. It contains the three vectors, three non-zero rows. So it's linearly, so it's a surjective. It's clear from surjective. For injective, you have to take its determinant. You have this 1, 1, 1, and you have the 0, 1, 1, and then you have a 0, 0, and minus 1. When you take its determinant, we get the value like this. It's 1 minus 1 minus 0, it's minus 1, and similarly we write the minus 0, the whole terms are 0, and similarly the whole terms are 0. So we get minus 1 answer, which is not equal to 0. So it's injective. So it's injective plus surjective, it's bijective. Is it clear? Hello?
Yes. Yes, yes, it's clear.
Now we have to find the T inverse. How can we find the T inverse? We find the T inverse by as we have, as you see that we have find the matrix T with respect to the usual basis, which is T, which is 1, 1, and 1, and then 0, 1, and 1, and then 0, 0, and minus 1. We take its inverse. As I told you how to take its inverse, we write 1, 0, 0, and 1, 1, and 0, and 1, 1, and minus 1, and we multiply it with the 1 0 0 1 identity matrix, 0 0 0 1, and our task is to make this matrix identity, and then this matrix is called the inverse of this. Is it clear?
Yes.
You can find the inverse by yourself, as I have
Yes. Yes.
told you. So the values you have got here, you look, this is the question 38. Now I am going towards the 38. So the kernel for in the 38, you in 38 he finds also kernel, so you can also find its kernel. So he checks injectivity by kernel method, but you can check by the other method, but you have to mention which method you are applying. You have to write the statement that if the matrix A is non-singular, then it's injective. Is it clear?
Yes.
You have to give the reason in paper, so why you are doing this step. In the second one, he finds in his, you see that makes the matrix and take its determinant, which is -1, so it's also linearly, so it's also injective, and it's surjective, so its inverse exists. And how can we make its inverse? We just take the inverse of this matrix, this one. You will see here, we take the inverse of the matrix. So inverse of the matrix, how can you take the inverse? You take the inverse, this is the inverse. You have taken this inverse, taken, you have now, this is the inverse of T inverse. How can you write it into the matrix form? You just multiplied with the it with the x1 x2 or x3, or another method is that the first element shows the x1, so it's x1, and then the second one here is 0 plus 0x2 plus 0x3. So first element is so into a triple pair, first element is x1, in the second it shows that minus x1 plus x2, and in the third column it shows that the x2 minus x3. It is the inverse of the matrix. Is it clear?
No. No.
No? Hello?
No.
No. Okay, I will repeat it again. Uh, listen, one thing, you always put the vector into column row form. This is the,
What?
I am saying that while making the matrix, put the vector into the row form. This is 1, 1, and 1 in this form. It's then 0, 1, and 1, and it's 0, 0, and -1 in this form. And
Okay.
when you take its determinant, its inverse, you see here, he take its this inverse by the method as I have told you. So to make it to write the trans T inverse, you write T inverse of x. You write here the, this is the x1 x2 x3, the coefficient of x1 1x1 minus x2 into comma, then the second row, you write the second row. This is the x1, the x1 is 0, so 0, the x2 is coefficient is 1, and the similarly plus the coefficient of x3 is also 1, and then comma, then the coefficient of last one, which is the uh, 0, and 0x1 plus 0x2 minus 0x3. You have obtained x1 minus x2, and you have obtained x2 plus x3, and then as you see here, as I write x1 minus x2, x2 plus x3, and minus x3, this is the inverse. Is it clear?
Yes.
Now you now moving towards the topic, he says that find the T inverse. We find T inverse. When you find the T inverse, then you have to find the T inverse of V. How can you find the T inverse of V? As you have find this T inverse, this T inverse, this T inverse.
Yeah, so we just put, yeah, yeah.
Is it clear?
So we just put, yes,
Just put the vector
yes,
v11 which
yes,
you obtained this result.
yes,
And in
yes, yeah.
similar way, you have to find this matrix, this thing which is t square minus 2t plus id. So you have to know the values of t by the matrix. So you have the obtained the matrix t. You take it from t3 and then you obtained minus 2t, then plus I. I means that identity matrix 1 0 0 0 and 0 1 0, and then operate this operation. You find this in x. When you find this in x, you just put v111 into this. Look here, for example, you see here he find the power t3, then he write t3 minus 2t plus id, and the answer is this. Is it clear? How can he solve this?
If,
Is it clear?
can you repeat it? I didn't understand. From where is it? Why is it ID and T?
You have to find the t3. As we know that he says that find this relation, find this
Ah,
relation.
yes, yes, yeah.
Now you have to find t3. How can you find the t3? As you have find this is the, as you have find this t. So multiply t, this is the t, multiply t with the t, you get t square. As you get t square, you multiply t square with t, you get t raised to power 3. Is it clear?
Yes,
So he do these calculations, and he get t raised to power 3, this one. Is it clear?
yes,
Now in the next step, he apply this one. He have want to find this thing. He wrote down the value of t3. He wrote the value of t3, then he write the value of minus 2 into the value of t, as which is 1 1, and then 0 1 1, and he write here the value of minus 2 into t. Then he write the id means that the identity which is 1 0 0 0 1 0 0 0 1, and then add, subtract, or do these calculation, you get this matrix. Is it clear? Hello, hello, hello. Is it clear
yes, it's
or
clear.
clear?
Yes, it's
Okay.
clear.
Now you have find the this whole result. Now you put, change, convert it into the transformation, like in the form of t of x1 x2 x3. How can you convert it into the t of x1 x2 x3? This is the coefficient x1 plus 3 x2 plus 2 x3. This is the first, and then x2 plus x3 is the second pair, and the third pair is minus x3. This is the t of, this is the, this term you have write this into the matrix form, and I will convert, just look, just wait. You have obtained this. I wrote this into this form, into the transformation form, which is of the form that you have obtained, we have obtained this one. You write it into the transformation form, which means that x2, and then which means that minus x3, and then x2. You obtained this equal to t3 minus 2t plus I into of x. You obtained this. Now you have to obtain the t of v. You replace x by v. Here x is 1 1, so you replace, here is v is 1 1, so here is 1 minus 1, and it's plus 1. So you get the answer into this form, 1 minus 1. So you have obtained the value 1 1 and minus 1 minus 1 and 2. Is it clear?
Yes,
Now moving towards the question 39, as we have done when we are finding its emission, secure emission, its unitary, complex structures or secure symmetry, orthogonal projection, as I have discussed today, tomorrow, yesterday in the previous days. And now we are going towards the 40, question number 40 shows that the linear transformation show that the linear mapping A T of A is equal to A transpose is symmetric. So we have to show that the linear mapping is symmetric. We have to find prove it's symmetric. Symmetric means that the matrix obtained A transpose it's equal to A. Symmetric
Yes.
means this. As in this case, he defines that A of T. So transpose of A is equal to A transpose. We have to check its symmetric. We take its transpose. Its transpose is A transpose into A. So A transpose into A is equal to its A transpose. So it's symmetric. In the similar way, but this question is not important as it comes in paper. So skip this question, I say.
Yeah.
This is not important. Now, question 41 is also not important.
Okay.
So we have today we have done the question from 30 question from 33 to 33, 34, 33, 34, 35. I will solve and send you 35. We have done 36, 37, 38, 39, 40, and then we have done until 39. But you can also look here for the symmetricness, but it's not necessary
Yeah,
because
it's not important. Yeah.
it's not important. Now we I think we have to start how can we find the orthonormal diagonalized basis. How can we find the orthonormal diagonalized basis as he asked in the number question number 37a part. It says that find an orthonormal basis. We have to find orthonormal basis, but to start this, we have an idea of orthonormal basis. So in this part, in this question 31, you look here 31. This clear out our idea of this question is about the orthonormal basis. How can we make the orthonormal basis? So to start orthonormal basis, you have an idea of basic. You have an idea of orthogonal, and you have an idea of inner product space, and you have also an idea of when the vectors are orthogonal, when the vectors are or normal. So to start this, this is a very complex thing. These are the complex things. To start this, you have an idea of what is an inner product space, what is the gram saturated product orthogonalization process. So we are going to start the question from 26 to onward. Um, can you wait for 2 minutes, 10 minutes so that I will eat some food?
Yeah, sure, sure. Okay.
Okay.